So the paper actually gives us an example, I realize right now, which might be enough to just, I think, close this series, because at the end of the day, I was like, so what is inside the box is G and D. So G is the generator and D is the discriminator. I mean, it's just really just models, right? I mean, at the end of the day, it's, I guess you can implement many things. So there's the paper links to other stuff like circuit-centered quantum classifiers. Maybe that could be, that's maybe a useful approach for the discriminator, because it's at the end of the day a classifier. So then this, each of those boxes really is its own, could be its own long series of videos. And the paper says, there's sort of so they've numerically tested the ideas in the paper with a simple example involving two labels, A and B. They chose a source R. So they basically, what they did is they have two labels, A and B, where A is 0, right? Because this is the notation for the for the density matrix for 0, and B is 1. So in their database of examples R, right? It's 0 and, so there's 0 and 1. The labels can be encoded in a 1-qubit label RG register, and the out RG register only requires 1 qubit. Blah blah blah. So they don't need the what they call the bath. Let me see. Here we have. Okay, so they don't need this bath thing in here. And these things can only, the label is, whether it's A or B, can, that's actually, it's nice. It's nice of them they provide this example. So what this is basically saying is we don't need, so RG basically just needs 2 parameters, and so this is the first thing. Why? So I'm just putting some dummy stuff in here so it doesn't get, because I think it, yeah. So this just needs, why it keeps telling me that it has Q1, Q1, Q2, Q2. Yeah. So really this is just this, and then we don't need here. Yes, I might actually need to redo the whole thing. Probably need to redo the whole thing. Let's see what they say. So don't need a bath register to generate entropy, whatever that is. The expected solution is that G should be able to generate a C0 gate conditioned on the label register. Yeah, exactly. So the what because what the G is doing is that it's trying to basically generate. It's trying to, you want to train G, the generator, to generate elements that seem like they belong to R, which is, we've got two labels, A and B. And so they're saying the goal here would be, because you have labels A and B, and then you could just simply say, well, G, if you give G the label A, then it should be able to just by means of a control node, choose. think that's what it means. We find that this can be achieved with 2 layers of the ansatz previously introduced. So they introduce a practical way of parameterizing these, which is basically this big thing. So this here, what you see here is the inside of the inner, the insides of G and D both. So both working this way. The idea is you want, it's a bunch of rotations. I see rotations of X and rotations of Z and rotations of ZZ. I don't know if that means that, I don't know what's that. Rotation ZZ. As a control, okay, no. Conditional. Since the generators of those gates are all simple Pauli operators, it is easy to implement the conditional H. So since if C's and Z's and ZZ's are between nearest neighbors qubits. Okay. So this is the inside of the generator and the discriminator, both kind of following the same pattern, right? So it's a, for the generator G and discriminator D, decompose in T layers. So it's like a generic, and then they're saying with this little example here, you would be able to actually, you just need a couple of layers. So 10 variational parameters. It's okay, 2 layers. Let's see what I would implement here. G discriminator requires at least 1 qubit for its output. So this discriminator, this is the generator. So let's 2 layers, 1 layer. Okay, 2 layers like this and this. So, and how many qubits we're talking about? This 2 qubit. It's really 2 qubits, right? Because it's only the label RG and the out RG. So this really it is. So this really it is like. So if I just for the sake of, so we're gonna say 6, and then we're gonna say this is here, and so this is really, it's not a Harmar gate. It should be easier if you, so it's rotation on X, rotation on X, rotation on Z, rotation Z, and then there's like a this here. What is a rotation? What is an RZZ gate? This is indeed something. 2 qubit ZZ rotation. Interesting. Phase shift gate in Qiskit. Qubit 1, qubit 2. What is it? C naught, U1, and a C naught? what is the that's a good one. Um, trying to figure out what is this gate in general. To keep its rotation. Whatever, so it's a C naught between 0 1. So that's how they implement it. So they, where am I here? So it's a C naught. It's a U1 with your parameter, and it's another C naught, and that's your. So actually, let me take that. Let's add here another one. We'll call this an RZZ gate, and there's Q and Q1 or Q, yeah. And so this is Q Q1. This is param, and this is Q1. I think this is it. So this is this, correct? Parameters and Q1, correct? And and so now you repeat that again. Rx, Rx, RZ, RZ, and this, and so this, and this should be, and this should be a north in the sense that this is two layers of this concept. Two layers of this concept, yeah. But now we have to parameterize them correctly. So this is mm, mhm. I don't know if maybe the best is to do this at the one layer level, because it's like 1 2 3 4 5 6 7 8 9 10, exactly 10 parameters, right? Yeah, maybe no, maybe that's actually at that level it's good enough. So so I would just say we turn all that thing into one big block, which we're gonna call M for model. I don't know. M for model or just model. And it's gonna be like this. Boom. So exactly, and then so it's gonna have Q. It's gonna have Q. Oh, come on. It's gonna have Q and Q1. And so all the Q4s are Q, and all the Q5s are Q1s. Exactly. Q1s. 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 And then, so this is, and this is parameters, I'll just call them, because these are all parameters, I will just call them Z1, Z2, or Z3. I mean, I don't know if you can just say that the parameter is, yeah, okay, Z3. Z4. Z5. Z6. Z7. Z8. Z9. And Z10. Okay. And so, I don't know if that works. Z2, Z3, Z4, Z5, Z6, Z7, Z8, Z9, Z10. I really don't know if that works this way. And so, if now I would do this, okay, it doesn't seem to work, but maybe this is just a limitation. Maybe there's too many, maybe, you know, just too many parameters for this. If I just to give it a try. Come on. Let me save and reload. Save and reload, because this doesn't seem to work. But you understand what is happening, right? So each of these gates has a parameter, and then what you're doing is 10 variational parameters, and these are the parameters you want to tweak, right? So and then it says, and then they say basically the discriminator requires at least 1 qubit for the output, 1 qubit for the label D, and it also presents 1 qubit out RG. We find that path D is not needed. D presents 3 qubits, and 3 qubits, 4 layers of the ansatz were sufficient to train the GAN. So this yields 32 parameters. Okay. Yeah, maybe I should just do 1 layer, and then it helps me. So with 1 layer, you would just have until done. What does it say, param? Save changes. Let me close all this other stuff, which is from other examples and other videos, and let me just do this. Have I just broken it? What if I start a new one? Okay. And then basically what I will do here is, let me start from scratch. So let me just add my gate model here. So I'm basically gonna copy this, and I'm gonna say so this is 1 layer. This is the alpha layer, and I don't know if I can. So I should be able to do Z1, Z2, Z3, Z4, Z5, and Q1. Shouldn't I? If I do like this, oh come on. Maybe this is a mistake. Maybe I should not parameterize it this way. Whatever, just to finish the example, I'll just clear at, and I'll say it's a layer, right? So L. Oops, oopsie. Let's assume maybe that I can do something like that. Maybe that's maybe that's the way that it has to be done. So this is parameter 0, 1, 2, 3, 4. Oh, come on. I think I have to, do I have to create a new one? So I have to create a new one, new circuit. No, close this one, close anyway. New circuit. And so this is going to be the subroutine called L, and we're going to add this exactly, and then it's going to be Q and Q1. Now it should work. What the? Q and Q1. Gate. Correct? So let's call this GAN2. Save. Q and Q1. Save. I don't like this. I don't know. Maybe I shouldn't just be. Come on, it worked in another example. So, maybe I should just. Maybe if I just copy. Maybe just copy the entire this thing. That should be then fine. Because then I can just, yeah, I'll call it L. Okay, that's good. Oh, seriously. Why? Is it like, is just something broken or what? What's going on here? What's going on here? What's going on here? Unsafe. I want a new example. Yeah, but it's like, it seems to be, there seems to be some issues right now. So, sucks. Maybe I'll just refresh the whole thing. Create a new circuit. Good, fresh. Fresh. Okay. Maybe. I know what I was doing wrong, I think. Because I was doing this in between the include and the declaration of the registers. Maybe that's why. Sorry. And maybe that's also what I'm doing wrong here all along. So we'll call this L. And it has all this stuff. And now please don't break. Okay, but it's just moved it up here. The thing is, I don't want to, if I double click on that and it's going to break again, then I don't know what's going to happen to me. I just wanted to see this inside, but come on, I'm going to try it again. Oh, come on. Damn it. Damn it, really. Is it just... Is it just this? Like, if I don't have this and I save and now I click, okay. If I do that, but this is on param. Maybe that's the problem. That's the problem. I'm so sorry, people. I'm so sorry. I know what's probably happening is that there's no... Maybe you can't use gates inside gate. Is it that the reason? Close anyway. New. Clear. Close anyway. New circuit. Okay. So if I copy first this, and I do it here, and then I put it somewhere and I click on it, no, it also doesn't work. Look, maybe I'm doing something wrong, but I'll just stay away from getting into the insides of this. It just seems to break the interface. Maybe I'm doing something wrong. I'll double check, but so let me just get through it. So this is however this is done, right? So this is one. um mm, 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 mm. Maybe I should check open chasm subroutines. No, that's the paper. I should probably use Qiskit and then let this be generated, and that probably should be the best thing that I could do. I just wanted to keep it simple and not get into code yet. So whatever. I mean, So this is what we're doing here. This R is this RZZ in here. And oh wait, I have everything here, and it seems to kind of be the circuit seems to be working. So no, I just spoiled it. Oh my god. Okay. Oh, really, people? Really? Okay. So I'm gonna build one layer again. New circuit. I'm gonna call GAN3. Save it. And so, it's a rotation in X, a rotation in X, a rotation in Z, a rotation in Z. And then there's this ZZ rotation, which is implemented with the control knot, a U1, and a control knot. And so this is one of your layers. And I wanted to simply pack that into a routine, right? And then say, so this is just pack. I want to pack this into a routine called layer, and just putting this here. Let's put layer, because if now can I add gates here? No, I cannot. No, I cannot. Param. If I do param2 and I double click, still the same. Dude, whatever. So so this is one layer, and I want to pack all in this here, and I'm going to skip now. So I'm basically you would need to have 5 parameters in here. So one for each of the angle is a different parameter, right? I mean, these I can do. So these I can pretend that this exists. Okay, that's definitely not going to be. I have to figure out. I might do a code example later. So you've got the 5 parameters, which are your angles, and then you've got 2 parameters, and then so each of Q3s in this case is Q, and exactly, and then each of these is Q1. So this is your one layer. Good. Good. So now G, so the generator, right? Call it G. It's just a 2 layers. So this is G. Okay, maybe I'll not make it a subroutine. G is 2 layers. The paper size is enough, as they proved in the results, in the experimental results. And it doesn't have this bath thing here, this last one. So it just has the label and it has the out. Then D operates in qubit reserve and bath D reserve that appear proof conversions, blah, blah, blah. D has 3 qubits, and so it has, and they say it has 4 layers, right? Am I correct? 4 layers. Perfect. 4 layers. So it's 1, 2, 3, and 4. So let's mark this. So this is R, and this is D, as a really practical examples. And you would see that, and you kind of see that each of the angles is one parameter, really, right? So and inside each layer you've got 5, right? So here you've got like already a considerable amount. So 30 parameters for a total of 42 parameters. And then we have the qubit register grad, which is for the gradient. The algorithm operates on 5 qubits, so that's what we got here. So actually it's even more like, okay, whatever. Let's ignore the last one. So it's actually 4. I mean, it's 5 different qubits, but when you plug them together, that's what it looks like. The GANs, training the GANs it's a delicate art. To keep this proof of principle simple, we choose not to use any advanced training heuristic. Training for the 10,000 gradient steps, we obtain rule 13. What is rule 13? Okay. With the learning rate, which exponentially decreases. The generated G is only updated once every 100 steps. Okay. It's so first the parameters are chosen randomly, okay, and right, quickly trendy generator should produce a decent state for the A label, but fails to produce a good state for the B label. Okay, so he basically explains what happens in the conclusion. So that's it. The only thing is that I don't know how to implement the gradient part. Because I don't understand that splitting here with this whatever Hamiltonian. Because other than that, it would be as simple as kind of like a Hadamard, right? A Hadamard, whatever control thing inside this box. So one like, and then here goes an X. And a Z. So here goes an X and a Z. And it's a control Z. Here the Hadamard. And then an H and a W and a measurement. And so another Hadamard, a sort of W gate and then the actual measurement. Exactly. I mean, that's how the gradient is measured. The way W is implemented is explained in here in a form that I don't understand. I mean, this is how you implement W. This is really how you implement W, which is this gate here. Okay, and H, and then I'm missing this part to finish up, but I think I'll keep that for the last part of the in the series. But I think that's the basic idea. So you see inside each box there's basically a model. It's and the way this is done is implemented in a generic way. And you can do this in it's implemented with this approach here, with this bunch of rotations, the X, Z, and then ZZ. Again, why this works? Well, let's put it this way. So those are generic. So it's you're rotating, right? So if you think about, you're rotating an angle X, or rotating an angle in the Z, and then so you can basically, I don't know why there's no rotation on the Y axis, for example, but because what I imagine is basically, and that's actually a really interesting concept, is that those gates allow you to rotate however you want in the block sphere, right? So in theory, that's why this is a sort of a generic approach to make a model, in that sense, because you can parameterize those angles and say, please rotate X this way and then Z this way, and then I don't know why, I really don't know why there's a ZZ in here, but I imagine you could just do like rotation over the X axis, over the Z axis, over the Y axis. And sure, that would not give you all the possibilities, but it gives you, it allows you to construct sort of any rotation in the block sphere, and so that you can use that as a model, because basically then you can just play with the you play with the parameters, of course. I just had like a bit of a, yeah, not so sure exactly why like an RZZ gate is used. uh, Maybe I'll investigate a little bit more. So in the last video, in the next video, I'll do the last one. I'll basically try to understand the two pieces that I'm missing. So we understand how those models work, right? We understand that those models work this way because you basically, so you're basically having you're building gates that allow you to rotate through the different axes. And then so you parameterize the angles, and you can let these learn, so to say, right? You start with random angles, and then of course it's not gonna generate what you want, but then you train it, and then at the end of the day it's going to generate what you want. And I think that's what matters. um, exactly. But and what I'm missing for the last video is the gradient concept, and why this is and how do you implement it using this approach. Exactly. That's what I'm missing. Cool. It's a tough one, but I mean, you grasp intuitively the concepts, right? Two models, one to generate, one to discriminate, and the funny thing is they're both implemented the same. It's just you're going to be tweaking them differently. And then you've got this gradient calculation, which is what allows you to like outside of the quantum algorithm, it allows you to recalculate the 42 different parameters that you have in the model until you get something that's what you need. And at the end of the day, here they're using a small example, right? So where the two possible labels are A and B. That's what you aim your generator to be able to create. So A is 0 and B is 1, right? So it's nothing fancy. But ideally you could have you know, different things in here. You could have like numbers, you could have like whatever else you want to generate, or images and whatever, right? So but that's the core idea. Cool.